Hello, it's great to see you all. The highest temperature scientists have ever achieved in a Large Hadron Collider is 5 trillion Kelvin. The lowest temperature a human has ever reached is 0.0038 Kelvin, equivalent to 38 picokelvin, or minus 273.14 degrees Celsius, or minus 459.66 degrees Fahrenheit. But is there anything hotter or colder than that? What does hotter or colder actually mean? Why is one hotter than the other? What is absolute zero? And why is its value exactly minus 273.75 degrees Celsius or minus 460 degrees Fahrenheit? The answer will be in this video. Energy is the foundation of the universe. It permeates everything in the universe and powers every body within it. In fact, 70% of the universe's energy is dark energy. More precisely, it is energy. There is a type of energy that scientists know is there, but they cannot interact with it. It sounds like something out of a fairy tale, doesn't it? Energy exists in many different forms and manifests itself in various ways in the motion of objects, in chemical reactions, and in natural phenomena. According to the world's most viral equation, E equals m*c². Even matter is just a form of energy, a highly concentrated form that you can touch and feel. If you weigh 70 kilograms, congratulations, you are equivalent to the explosive power of 1.5 billion tons of TNT. That's 30 yellow bombs, or 100,000 little boy Fong grenades, if you're still not impressed. Humans and many animals sense heat through sensitive nerve endings called thermoreceptors. They are sensitive enough to distinguish temperatures from minus 10 degrees Celsius to 60 degrees Celsius. But the problem is that a kettle of water, whether frozen or boiling, still contains the same number of water molecules. The coarse formula remains H2O. So why do they have different temperatures? The core of temperature lies in the movement of atoms and molecules. All atoms and molecules are constantly vibrating, even if they are atoms in a lump of iron or a diamond. And if you remember, anything that is in motion has energy. It's called kinetic energy. Kinetic energy is directly proportional to the mass and velocity of an object. Therefore, the faster an atom moves, the greater its kinetic energy and the higher its temperature. Thus, the temperature of an object is the average amount of kinetic energy of the molecules that make up the object. In other words, the faster the molecules that make up an object move, the greater the average kinetic energy of the object, and the hotter the object gets, and vice versa. When you heat a block of ice or a steel bar, the elements that receive energy will vibrate faster and faster. And if at some point they were to separate, they would almost certainly be in a state of literally free drift. That's how rocks melt, how iron and steel melt. But there's a problem that few people notice. Increasing the temperature is always much easier than decreasing it. You can easily boil water to 100 degrees Celsius. Light a wood-burning stove, and you can create a fire of about 600 degrees Celsius. Add coal, and you can melt almost anything in your house with a 1,900 degrees Celsius fire in just a few minutes. Hey, don't try this at home, kids. Conversely, you need a refrigerator and several hours to create an ice cube with a temperature of around minus 10 degrees Celsius. Why is that? Why is it so much harder to lower the temperature than to raise it? And why is temperature the only measure of temperature? It has a negative value. Why do you have minus 10 degrees Celsius, but not -50 m or minus 1 kilogram? Please like this video to buy a ticket back to 1714. That was the year when the Polish-German physicist and inventor Gabriel Fahrenheit created the temperature scale that bears his name, now known as the F scale. Fahrenheit established his red scale by creating 3 fixed temperature points. He placed the thermometer in a mixture of ice, water, and ammonium chloride. At the point where the sundial reading drops to its lowest, Fahrenheit takes 0 degrees Fahrenheit as the reference point. The second reference point is the thermometer reading at the temperature of the water just before it freezes. Fahrenheit set this temperature at 30 degrees Fahrenheit. The third calibration point, 90 degrees Fahrenheit, is defined as the normal human body temperature, i.e., the reading on the thermometer when placed on the wing or in the pad. Today, in the Fahrenheit scale, water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. The normal temperature of the human body is 98.6 degrees Fahrenheit. The Fahrenheit scale was the most important temperature scale in English-speaking countries until the 1970s. Today it has been almost completely replaced by the Celsius scale, except in the USA, where the Fahrenheit scale is still stubbornly used alongside the English system with cumbersome units like p, inch, and food. The Celsius degree unit was first proposed by the Swedish astronomer Anders Celsius in 1742. It's the opposite of what you know today. Water boils at 0 degrees Celsius and freezes at 100 degrees Celsius. Later courses reversed it, but retained the name in honor of Celsius. Clearly, the Celsius scale is simpler, smarter, and more suitable for everyday life. But both of these temperature definitions have a drawback. They are too far removed from the scientific definitions of temperature that Vivek just presented above. Temperature values in both the Celsius and Fahrenheit scales are approximate, meaning they are for convenience only and do not follow any scientific rules. From a scientific standpoint, temperature, like length or mass, does not have a negative value. The lowest possible temperature would only be 0 degrees Celsius. And no, Dew still views it from a scientific perspective, like the speed of light. Everyone craves it, but there's no way to achieve it. In reality, absolute zero is a sight you wouldn't even dream of seeing. Unless you have a terrible memory, you probably still remember that temperature is directly related to the vibrational motion of the constituent particles of matter. The slower the particles swing, the lower the temperature. Logically, there exists a temperature point at which all motion ceases completely. That is essentially absolute zero. But why is absolute zero considered unattainable? What do we want to achieve absolute zero for? And what's so special about absolute zero that we've been talking about it so dramatically throughout this video? Absolute zero can be easily achieved in the imagination by assuming that all particles of matter cease to move. And this is where things get really creepy. In 1802, the French chemist and physicist Josephus discovered that at constant pressure, the volume of a gas changes proportionally with temperature. Specifically, when the temperature changes by 1 degree Celsius, the volume of a gas changes by 1/273 times its volume at 0 degrees Celsius. To put it simply, this finding means that when any gas is cooled down to -273 degrees Celsius, its volume will be zero, meaning it will disappear. Yes, a word that science hates: disappearing. If it were an ordinary person, they probably would have crumpled up that ridiculous calculation and thrown it in the trash. Superstitious people have probably promoted it as the formula of the serpent demon, the end of the universe. But no, Gay Lucia was a scientist, and he came to a different conclusion. -23 degrees Celsius is the lowest temperature in the universe. Unexpectedly, he was right and even said it loudly. Later, the British physicist and mathematician William Thomson, also known as Baron Kelvin, developed an absolute temperature scale without any negative values, known as the Kelvin scale. On the Kelvin scale, 0 degrees is equivalent to absolute zero. To convert degrees Celsius to Kelvin, simply add 273.15 to the temperature in degrees Celsius. For example, 0 degrees Celsius equals 273.15 Kelvin. But the more important question is, what is the true nature of absolute zero? 0K is equivalent to -273.15 degrees in Celsius or -459.67 degrees in Fahrenheit. But why do atoms and particles have to stop at zero at precisely -273.15 degrees Celsius and not some other value? The answer is only God knows. The precise value of absolute zero is one of countless values that seem to have been fine-tuned and preset for the operation of the universe. Just like the speed of light, the mass of an electron, or the number of spatial dimensions. We shouldn't and analyze them further except by accepting that this is how things work in our universe. But what happens to matter when it approaches this temperature limit is something we know. As the temperature increases, the atoms accelerate their separation from each other and float freely, turning the solid into a liquid. This continues to happen as temperatures rise further. Matter, when in a state of extreme confinement, even in liquid form, expands and vaporizes, then even turns into plasma, a strange yet wondrous form of matter. Most of the matter in the sun and stars exists in a plasma state. Music, in fact, plasma, not solids, liquids, or gases, is the most common state of matter in the universe. Conversely, if we conduct a reverse experiment and begin to decrease the temperature, the cooled particles will begin to slow down, condense into a liquid, then solidify and become a solid. Inside a solid, the particles are very close together, neatly arranged, yet they continue to vibrate. Furthermore, the temperature will cause the solid particles to vibrate less and less until it almost stops completely. And importantly, you have to remember those two words, which are almost like saying you would need infinite energy to propel a cosmic sphere to the speed of light. Absolute zero is simply unattainable. Energy is neither created nor destroyed. It simply frolics from one place to another, from one form to another. When an object is given a command, for example, the lonely heart of a single man in the freezing cold of winter, it will release heat into the surrounding environment. The problem is that the closer an object gets to absolute zero, the less heat it emits. This means that the lower the temperature, the less effective and more energy-intensive the cooling process becomes. According to the principles of heliodynamics, you would need infinite energy to cool down to absolute zero. To put it simply, becoming a Type 3, Type 7, or Type 7 times 753 civilization is easier than creating absolute zero. In addition, there is another problem. At 0R, the zero authenticity, the measure of the degree of entropy chaos in MO, and the third law of anthropometry forbid this. Furthermore, if the particles stopped moving, that is, if they were at rest logically, we could simultaneously determine both their position and momentum with precision. The problem is that the two-step uncertainty principle, one of the fundamental principles of quantum mechanics, doesn't allow for that either. In short, absolute things are like a doll in a glass case. You can only see it, talk about it, but you can't touch it. That's all. But there's no need to be sad because the best things are always at the absolute limit of the deep freezing process. Scientists have discovered amazing, unimaginable properties that defy the usual laws of physics. Specifically, very close to absolute zero, some metals almost completely lose their electrical resistance. They became the ideal conductors in legend, allowing electricity to flow through them with virtually no loss. This is known as superconductivity. The atmosphere was equally solemn. Helium gas turns into a liquid at minus 269 degrees Celsius. As the temperature continues to drop, a phenomenon that seems almost magical occurs. Viscosity refers to the ability of liquid helium to resist flow, which is zero. When you pour water into a glass, the water stays still in the glass. That's the way life is, isn't it? But when you pour superfluid helium deeply into a glass, it flows. More precisely, it's the liquid leaking through the tiny capillaries and gaps in the glass elements down to the bottom of the glass and falling out. A thin layer of heli can climb over the sides of the container and leak out, forming a droplet at the bottom. It can also create a frictionless fountain that can flow on its own forever. And if that's not magic, then what is it? Offer prayers. Finally, near absolute zero temperatures have allowed scientists to discover a fifth state of matter, which will likely be included in the high school curriculum in the future. Congratulations to you all. It's okay. God bless you. God bless you. Specifically, the existence of a fifth form of matter was predicted in 1924 by the well-known figure based on the quantum formulas of the Indian physicist Sandra B. It is known as Einstein's condensed matter. Namna. Einsteinian condensation is a state of matter in which isolated atoms or subatomic particles move so slowly that they pile up on top of each other, condensing into a large cloud and acting like a giant atom. Its existence was experimentally confirmed by Eric Cornell and Carl Wieman in 1995. At the Joint Institute for Astrophysics in Gila Laboratory, Cornell and Wieman successfully merged approximately 2,000 individual atoms into a superatom large enough to be observed with a microscope. And if you experience headaches, dizziness, or lightheadedness on your own, that's okay too. If scientists have been struggling with quantum mechanics for over 70 years, what are we compared to them? But as our elders said, with money spent and effort put in, even the most ruthless strategists will eventually succeed. In 1999, female scientist Lynn H. used a fifth form of matter to tame light, bringing the cosmic steed back to the speed of a motorcycle, approximately 64 kilometers per hour. Even more astonishing, scientists using the condensed matter have been slowed down light from 299,792,458 meters per second to just 0.2 millimeters per second in 2008, and even stopped light for 16 seconds and then for a full minute in 2013. Oh my God! Wow! We cannot know for sure how scientific discoveries at near absolute zero might change the future of human civilization. But I'm sure that a like from you guys can make us laugh like the baby's father. As always, remember to subscribe to VF and turn on notifications to stay updated on our mind-blowing science content. And now, goodbye and see you again.